So any questions on that? Was there any terms in there that you don't understand? So terms is a lot to do with it. And this section right here, we're going to cover a bunch of the terms. Now, I don't know if y'all noticed or not, but it's become common practice for just about every manual you get, even if you go out and buy a TV and it comes with a user manual. What's the first section of the manual? Safety. You see these robot safety portions, they're really long. They're just about everything you buy in it. I bought a new electric toothbrush, and it had safety in there. It's the very first thing. Robot safety. These are robot safety standards. The main one is originally started out with the Robot Industries Association, what they call the R15.06. So most people just call it the 1506 standard. This was adopted by the American National Standard Institute, which is referred to as ANSI. Canada has a standard. And then, of course, we've got international standards. And what's happened is the IRA standard, which originally set it up, has been adopted by the international standard, the 10218-1 and the 10218-2. So odds are, if you get out and you go to work for somebody that has a lot of robots, you'll have to attend some training session on safety. Basically, the 1506 standard is divided into two parts. The first part is basically dedicated to manufacturers of the robot, and then the second part is the robot system and integration, which would be where we as technicians would fall into place, not unless you go to work for some place that makes robots. So this is a definition RIA has established for an industrial robot. It's an automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes, which may be either fixed, in place, or mobile, which they added that term lately for use in industrial automated applications. So you don't have any questions about these terms? Everybody understand all those terms? Yes, no? Don't know, ask. Everybody okay? Space. This could be called the workspace, or it could be called the robot space. So those two are interchangeable. These are 3-dimensional volumes encompassing the movement of all robot parts through their axes. This was previously called the robot envelope or the robot workspace. It was called the robot envelope or the workspace envelope. So, are you okay here? This is where we start having problems. So, what we do is the space the robot moves in, or has the capability of moving in, has three different terms. The first one is the maximum space. This is a volume or space encompassing the maximum design movement of all robot parts, including the end effector, which is also known as the end of arm tool, right? We've already talked about that. Work pieces and attachments. So that means that's it. That's as far as the robot can get out to. Okay, and that's in all directions, right? Then we have what we refer to as the restricted space. So all our robots are operating within a restricted space. Even the big FANUC. We have some hard stops on the big FANUC that prevents it from running into the walls and getting into the glass over there. So these two guys are different, right? So the restricted space is the portion of the maximum space to which the robot is restricted by limiting devices. The maximum distance the robot, end effector, and workpiece can travel after limiting devices activation defines the boundary of the robot's restricted space. Do y'all understand restricted space? So these are good test questions right here. Then within the restricted space, we have what we call the operating space. The operating space is the portion of the restricted space where the robot actually operates. So if we look at our robot, it's definitely that these robots can reach out further than what we allow them to do. So we have a restricted space. Ours is restricted by a plexiglass. But we never ever going to hit the plexiglass. When we write a program for this robot, it's not going to get up against the plexiglass. We're going to write programs that are within an operating space, right? You understand? So your operating spaces are that section within the restricted space that you write your programs. Safeguard space. This is a space divided by parameter safeguarding devices. So we might restrict the robot, but then again we might have a fence around the robot, right? You understand? And the fence around the robot might be bigger than the restricted space. So the restricted space is where we restrict the movement of the robot. And then we safeguard outside, right? Y'all understand that? So the safeguard space, so our restricted space and our safeguard space are pretty much well the same. And we can see the safeguarding devices when we go over there and take a look. Any questions? Some of them you can see, some of them you can't see. Are we okay? Everybody okay?
Yes.
Okay. Everybody okay on the 3-position enabling device, also called a dead-end switch? And what are the 2 locations required by the 1506? Required. You had to locate them. That was part of your lab over there. You said, okay, where are the e-stop buttons at? Where were they at? Huh? One on the T-spindle and one on the controller. So those are required. The IRA says that everybody in the workspace needs to have a 3-position enabling device. So this would be one of the portables that you would wire up, or the technician would wire up. Now we don't teach this in this class, but if you take the industrial robots, we'll get into how to add safeguard devices and how to add emergency stop devices or 3-position enabling devices to the work cell. And it's not hard. Safety-related stopping circuits, these are not normal stopping, so every one of these robots have a button on that fleet spin that you can perform a normal stop. Some of them call it roll, some of them has 10 up there, some of them call them stop. That's the button you're supposed to use to stop the robot. Emergency stop. Emergency stops we only use in what? Emergencies. So if something happens, the robot goes wacky, and it can happen. I've never seen it, but I've heard about it. Or something's happened in a program, and programs crash. These are programs, these are computers. They have glitches in them that happens. They safeguard it as much as they can. And then our safety stop, our protective stops. Why 2 types of stops? What they call this on the video? Redundancy. What does redundancy mean? Repeating or more than one way, right? Okay. So redundancy. We was talking about in my other class, the space shuttle had 5 computers on making decisions on what to do. And why did it have that 5th computer? To break the tie. So that was the guy that if your computers started disagreeing with each other, that may agreement. We have 100 people in the Senate. Well, that's an even number, right? You understand? But there's a built-in safety feature, so there will never be a tie in the Senate. Who's that? Y'all don't know. You're talking about the House of Representatives. The Vice President of the United States is over the Senate. He is the 101st person. That didn't sound right. So he's the tiebreaker. So redundancy means we do things over and over and over. Airplanes have redundancy all in them. So they have backups for the backups. Some of them have a lot. You know, most airplanes have at least 2 redundancy systems that come into play when they fly. Our plane was fled. The plane I worked on was a fly-by-wire, but it also had cable. It had a cabling system in it. So when everything was working okay, the pilot had force sensors and everything in the yoke and the pedals and everything. So the pilot was inputting the information into a flight control computer, and that was what was flying the plane. But if something happened to that computer, they had these disconnect panels. They could jerk up, and then they took control away from all the hydraulics, and they flew the plane by cable. So they still had the cables hooked up. So that's a redundant system, right? You understand, if something goes wrong with the other one, then. So that's why we need two types. All our safety and e-stop systems in robotics is what we call control reliable. Control reliable safety circuits shall be designed, constructed, and applied such that any single component failure shall not prevent the stopping of the robot. So basically that means there's 2 of everything. You might see one, but there's actually 2. That e-stop button is 2 switches. It's not 1, it's 2. They're just done by the same actuator. For each set of switches, we have a different electronic circuit. So there's 2 electronic circuits monitoring these e-stop and these safety devices. So if one electronic circuit fails, then the other one's going to pick it up, right? You understand? So your e-stop circuit and your safety circuits these are what we call control reliable stuff. The circuit shall be hardware based, so that means even if you do a lot of safety stuff, this guy was talking about ultrasonic sensors and all that kind of stuff. That's great, and these work good, but the safety and e-stop circuits have to be hardware based. You know what hardware is? Huh? Y'all been reading those? What is hardware? Hardware means you got to be able to touch it. So an e-stop button cannot be a little touch button on a CRT somewhere. You can't be it because that's controlled by software, right? You understand? E-stop buttons have to be hardware. They cannot be computer based because computers have problems. Computers lock up. Well, what if your dang computer locked up and you can't stop it? The e-stop button on your little old touch screen don't work anymore. Now, we do a lot of stuff with those computer screens, but your safeguard and your e-stop circuits have to be hardware. They have to be mechanical. So control reliable is best described as dual channel with monitoring. So dual channel means everything's in 2s, right? If one fails, if both of them fails, you're screwed. It's like having a plan B, A and B, and not having a C, right? When a fault occurs, a safety function is performed. When a fault occurs, a safety function is performed, and a safe state shall be maintained until the detected fault is corrected. So that means basically, okay, I've hit the e-stop button. Well, that e-stop button doesn't pop back out. It latches down. And you can't just pull the e-stop button back out. You literally got to turn it, push it back in, turn it, and unlatch it. safeguard circuits, if the door is open, the fault always what? Exists. Until you do what? Until you close the robot work cell back up. And for reasonably foreseeable faults shall be detected. So some faults can't be detected. So this is what we're doing. These are our objectives: to be acquainted with robot safety, understand safety standards, recognize safety reliability, be familiar with human factor issues. The human factor issue is something that you won't believe what people will do to get themselves killed. It's like people running red lights. I mean, they'll run that red light, and what did it save them? You know, maybe a minute or two, no more than 2 minutes. And they're risking their life for 2 minutes. Texting while driving. You're risking your life so you can chat with people on a cell phone. And so this is what I'm talking about. It's unbelievable what people will do to get themselves killed. Hopefully you're not one of those. Hopefully if you get a text, you just ignore it. If you get a cell phone call, you ignore it. My wife's the kind of person that if the phone rings, she thinks, by God, it's got to be answered. And I keep telling her that. Of course, that's why I got a little ear. Now she's got one of those where she can talk without stopping. Be aware of safety sensors and monitoring, realize safeguarding, perceive the important factor of training, apprehend safety guidelines, and understand definitions. Because these manuals are written using the definitions that we're talking about here. And that's why I wanted to ask if anybody had questions, because that guy was throwing up there, he was throwing out terms that we're going to use this semester. We've already talked about the end effector, right, the space, and that kind of stuff. Are we okay? Of course, if you take the intro, we'll play around with ultrasonics and some of the sensors. Three differences between robotics and conventional machinery can be identified. Speed of movement, predictability of movement, hazard of movements. A lot of people think they realize what the robot will do, and they wasn't involved with the program. And most of the people that program the robot know all the moves that the robot might make. But you got to understand, these guys are sensing their environment, and they can do different things than they normally do. So if something happens that don't normally happen, but it's been anticipated by the programmer that it might happen, then they might have that robot do something that you're not used to seeing it doing, right? You understand? And then you get in that robot's way, and it's doing a high-speed move. There is no way in the world you're going to get out of the way of that robot. We had on the planes I worked in on the Navy, it had a Bombay door on it. And it used 3,000 PSI, had 2 actuators, and that sucker would close in a heartbeat. And of course, the story they told was a guy was in there and the Bombay doors closed on him, but it didn't kill him. It cut him in 2, but it pinched him together, and it did kill him. So they came in and they called the guy's family in, and they came in and let him talk to him, because they knew when they opened the door, he would die. Okay, that was a good story. Then I got to U.S. Steel, and the story changed to a guy got caught between the couplings of the train, but it was exactly the same story. And then a movie with Mel Gibson. What was that one? Yeah, his wife got pinned between the car, and they knew when they moved the car she was going to do what? Die. So I realized that wasn't a true story, but it was pretty interesting. So you need to recognize those, right, and predict the movement. Predictability of the movement. That's the problem with a robot. The movements are not predictable. It's up to the programmer to decide the movements, right? It might see a piece of equipment come in, your detection systems. It might do several products, and it might be running this product for 1 week, and the next week they switch over to another product, and now the movements of the robot does what? change. In conventional machinery, hazard zones may be difficult to recognize, but are fixed with time. And this is the problem with robots. Their movements are programmable, which means they can what? Change. I mean, you're going to write several programs this semester, and every program is going to give a different movement. So that's the problem. Most automated machines do the same thing. I mean, that's all they do. To do something different, they have to be redesigned and Also, the main difference between conventional machinery and robots is that robots can be programmed to do different jobs, react to changes in the process, even making decisions from a limited number of choices. And this is what we've already talked about. You know, just because you've been working there for a while and the robot's always been the same thing, that doesn't mean it's not going to all of a sudden do what? Something different. Because something happened in the work cell that you just hadn't seen before. And the human aspect, this is the human aspect. This gets more people killed in industry than anything else. It's that humans don't follow the safety procedures that the plant has established. They don't follow to save a little what? Time. And then they end up having no time. Robot safety must include the useful consideration of man, machine, workstations, environments, and behavior. Even when they was talking about the fences, you know, they said the fence needs to be high enough so it would make it hard for people to climb over. But they know people are going to do what? It's just like the top of our work cells were open. And in the simulation class, we're going to simulate, do a 3D model of the simulation of the motor man robot. And so you got to you got to measure everything, you know, if you're going to draw it. And so you'll climb up on a little step ladder, and people will be trying to work on measuring stuff, and somebody's trying to run the robot. They could get into the robot work area, right? So engineering deficiencies, lack of proper procedures, and that's what gives an inadequate programming. Hopefully you won't do inadequate programming. These are, you know, programs that are not safe. Emergency stop switches must appear on the control panel and also added to the pendant, right? And then everybody in the work cell should have a teach pendant. It's real hard for most people to get into our work area, but it's also hard to get into our work area with the teach pendant. So, y'all doing things, remember the person that is controlling the teach pendant is controlling the work cell safety. You'll understand that. And of course, that's when a lot of accident most of the accident in robots occurs during the teaching operation, teaching and maintenance. And usually maintenance is guys fall off stuff. But teaching, people will be in there with the work cell and not be cognitive of things that's around them, right? You understand? And something will happen. You know, they'll stick their hands in there and try to move stuff around while the robot's in motion. And the robot has no idea that your hand is there. The operator does. But humans don't respond as fast as they think, right? Unfortunately. Level 1, so these are our levels of safety. We have 3 safety levels. Level 1 is the workstation parameter. Level 2 is within the workstation. And level 3 is adjacent to the robot arm, which means you are in the reach of the robot. And we have different sensors that we use depending on what level of safety you're looking at. Installing program, operating, maintaining the robot. Safety can also be considered as a judgment of acceptability of danger. When danger, and so one of the assignments you're going to do is you're going to develop a set of safety rules. And it always gets me sometimes. Safety rules are not Rich's rules. Safety rules are what you do to try to stay safe, right? You understand? So a safety rule would be like, wear your safety glasses and stuff like that. It's not going to be turn on the air before you do this and turn off the robot. That's just a procedure. That's not safety, right? You understand that? So a safety rules are procedures that you follow to avoid accidents. So I think it's a minimum of 10. You can do more. You can't do less. And when you do that, don't cut and paste. Don't cut and paste. The college has got a new procedure with Blackboard. It's called Safe Assign. What Safe Assign does, if I highlight your text, it scans the internet and looks for those things. And they demonstrated this in one of our faculty meetings, and it was amazing. I had one guy that submitted a paper, and 99% was out of a document that was already on the internet. And what grade did he get on that paper? Okay, it's called Safe Assign. So I could rip this stuff out and I can insert it in the Safe Assign, and I can see if you cut and pasted those suckers off the internet. Plus anybody else that's been in this class. So it scans for documents here on the college and plus on the internet. So I don't mean you can't use those as a reference, but by George, you better put them suckers in your own words. And your own words don't mean changing one word. It means in your own words, right? You understand? So don't do that to me. I'd hate to kick you out of the college, but cheating is something that I just don't tolerate. And you're in a trade. You're trying to learn a trade. To me, I don't condone cheating, but to me, it'd be more logical to cheat in a math class than it would be to cheat in a trade that you're trying to get a job in, right? So, but it amazes me what people do to cheat. They put more work in cheating than they do if they did the work. So I've got a few stories. So don't cheat, don't copy things directly out of books. Because if it's out there on the internet somewhere, Safe Assign to find it. Hazard. Hazard is defined as an injury producer. And risk is defined as a probability that an injury will occur. A hazardous situation that has come to pass is referred to as an incident. And this is what the people at plant safety do. They try to look for safety hazards. Either if they remove the safety hazard or they come up with a procedure to try to avoid an incident, right? Out of U.S. Steel, we had SJPs, Safe Job Procedures. And almost every time when we came into work, when we got there, they had a set of SJPs we were supposed to read, but we signed off saying that we read them. And basically it was set up, even on how to use a screwdriver. So they had how to use a knife. They had SJPs for everything. So basically, if you got hurt, whose fault was it? Yours. And most of the time it's true. This is what in robotic environments, parts or bodies being caught. We call these pinch points. Being struck by part of a robot falling from the equipment or structure, like the guy that got killed by the roller coaster a couple of weeks ago. Climbed over a safety fence looking for his wallet and his cell phone and got hit by the roller coaster because it was one of those under the bottom roller coasters that you didn't ride on it, you were strung from the bottom. So undoubtedly the tracks looked like they were real high, but when that roller coaster came around, those people was way down, close to the ground. And after his cell phone and his wallet, climbing over safety barriers instead of going telling somebody, you know, I lost my wallet out there, I need to. And they'd have probably took care of him. I'd imagine they would. Falling from equipment or structures, this deals with a lot with maintenance. People will climb on robots and stuff like that and not bring in stands because it takes a little more time to bring in a stand or a ladder, and they'll climb up on the robot and slip off. Slipping or tripping or walking on working surfaces. Exposure to dangerous levels of heat and electricity. There's very few electrical items that don't get hot when they're working. Excessive physical strain. This happens a lot. People try to pick up more than they were designed to pick up and strain their back. Are we okay? Safety standards are very important in the workplace. All professional associations have defined the following priorities to eliminate. Eliminate the hazard through machine design. So a lot of the design of equipment is basically they're trying to design that to eliminate or reduce hazards. Apply safeguarding technology. Use warning signs and labels. Train and instruct the worker, programmer, and maintenance personnel. Now, robotics is unique. So in robotics, a robot technician basically does all this. The robot technician is usually responsible for programming it, and they're usually responsible for maintaining it. So you have to know your robots, right? So you're responsible for doing the preventive maintenance on the thing. You're responsible to fix it when it breaks, or decide what's wrong with it and then fix it when it breaks. And then also responsible for programming. Now you might have workers around there that enter or have access to the work cell. So what they try to do is they try to minimize the human factor. You will never, ever, 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 ever eliminate the human factor. It's just like that pilot that flew that commercial airline into the mountains. That's human factor. There was nothing wrong with the plane. The plane was in perfect operating order. All the reliable, everything was set in place in that airplane. And yet the human factor came into play, and the guy decided he wanted to commit suicide and kill all those people. And that's something we cannot do away with and get rid of, is the human factor. So like what they try to do is minimize the human factor. By the way we lay out the control panel, or the way the teach pennant's laid out, personal training, barrier guards, safeguards, interlocks, and warnings. Of course, we don't have any warnings on our robot, but they're really small enough, and you're using the robot, so I guess we should put one on the manufacturing line over there. It could be running and somebody could get hurt on that. But in the Big Fanic, we don't ever run it. We don't have safeguards on the Big Fanic. We do have some limiting hard stops on it to keep it from getting into the walls. So that's why basically when we run it, we don't run it. We never run that robot in automatic mode. That robot has what we call a high-speed teach. A high-speed teach, what's the limiting speed for jogging a robot? The maximum speed. 250 millimeters per second, which is roughly 10 inches per second. Some of the robots, the KUKA and the Big Fanic has what they call a high-speed teach, which has nothing to do with jogging the robot. What it does, it allows you to run the program in manual mode at full speed. So the Fanic has what they call T1 and T2. And if you look at T1, it says 250 millimeters per second. If you look at the T2, it says 100%. Now the 100% is not when you're jogging the robot. The 100% is when you're executing the program with the teaching manual. So that means to run it, you got to have the deadman switch pressed. Of course, I was doing some reading, and what they're trying to do is why they like T1 on these production robots is so they can actually get the true cycle time for the robot. And one of the main cycle time, probably 99% of robot in manufacturing, probably around 90%. The programs are repetitive programs, which means they do what? They come down, they do cycles. They'll start in a home position. They'll come down, they'll do something, they'll move around, then they'll come back to the home position and wait on something else, and then they'll come back do it. And what they do is they come up with a cycle time. And one of the ultimate goals of the programmer is to make the shortest cycle time possible. Because I didn't show y'all the video, but I did my class last night. When they make these work cells in the Kia plant, when they move into they got to get through the assembly section, which means they got the whole frame assembly in 90 minutes. When it comes into a robot station, it's in there for 60 seconds on each one of those stations. So you got 6 robots that's got to get in, do their job, and get out within what? Yeah, and then when the robots come out, it'll move down to the next station. And then they'll clamp that thing down, and they'll add another piece to the frame, and then these robots, so they're putting out, they're moving to that thing. I'm sorry, I need to go back and look at that. How long it takes to go through that thing. It's unbelievable. But the human factor is just something, and hopefully we don't have to run into the human factor in this class. Are we okay? Safety monitoring involves the use of sensors to indicate conditions or events that are unsafe or potentially unsafe. So the safety sensors that we have we got some of them are software controlled, some of them are hardware controlled. Like for instance, on all the robots, we have the ability to set what we call the torque limit on the robot. So that's how much torque the robot can produce before the motors burn up, because they never do, because it's always going to hit a torque limit before it cuts itself off. And some of y'all will see that. The motor man, and the problem is the motor man. It's fairly complicated, and we need to figure out how to do it. But the motor man's got a lot of safeguards on it, and what you'll see is it'll pop up a lot if you're on it. And a lot of the distances that we have set on our lab was set by the rotor or by the motor man, because it gets out of the safeguard limit so fast. So if you get some of those, we'll just look at it and see what we can do. But you got to go in. They call them S parameters. And you got to do a little math, and I just hadn't had time to go out and figure it, even though the robots have been here since 2008. The objectives of safe monitoring includes not only the protection of the human who happens to be in the cell, but also protection of the equipment in the cell. And this is not on y'all know what the work cell is. What's the work cell? Nobody knows what a work cell is.
That robot works in.
It's everything. It's not but it's everything the robot that's mounted on the robot or mounted in the space that it's in that it can get to. Everything is considered to be part of the work cell. So what we're talking about is we're talking about equipment, not only equipment that's mounted on the floor and stuff or the ceiling, it's anything that we have mounted on the robot. So you look at the big FANUC, that sucker's got a lot of stuff mounted on the robot. Right, you understand? And we're talking about some the weld head on that thing, there's no telling how much that thing costs. And it's got to be perfect, because it's got to make the same weld every time. And you swing that thing around and you bend that tip a little bit, well, guess what? Now you've got big problems because you just damaged. So the robot, I'm sure they can replace them, but you can cause a lot of money damage and a lot of time. But what we're trying to do is these safety to monitor devices are not only there to protect you. Sometimes we actually put them in there to protect the work cell too. Simple limit switches to sophisticated vision systems that are able to scan the workplace for intruders and other deviations for them. I'll try to find we got a video where I think it's ABB has put out a package called Safe Area. And what it does is it allows the robot to operate in an open area. So you don't have to fence it in. But it uses camera systems. And what the camera systems does, it sets the speed of the robot depending on how close the person is to the robot. So when you first enter it, it might slow down a little bit. And the closer you get to it, the robot runs slower and slower and slower. And then if you get up to the robot, it stops. Which is a pretty unique system because the robot is still in production, but it's going to drop down to a speed that makes it less lethal, right? You understand that? I'll see if I can find that. It's pretty neat. It's a video on YouTube too. So a lot of special limit switches. We could use sophisticated vision systems, but your emergency stop and your safeguard circuits have to be mechanical, right? Care must be taken in the work cell design to anticipate possible mishaps that might occur during operation. Are we okay? Y'all can read these as good as I can. Here's our levels. Level 1, level 2, level 3. Y'all look those over and see if y'all got any questions. Or I can read them to you. We got it? Any questions on those? Huh? Any questions? Yes? No? For sure, y'all know y'all have access to these PowerPoints on Blackboard. So usually level 1 is out on the workstation parameters. So these would be your fences and everything that you set out on the parameter of the robot. Level 2 is when we come into the work envelope. So these would be here, these would be your safeguards on your gates and everything, which detects when somebody enters the robot area. And then level 3 would be if you get in the reach of that sucker. And they have different sensors that basically detect that. By the way, I don't think this brings it up, but it's required that the robot controller be outside of the maximum space of the robot. So it's got to be out far enough so no matter what happens, the robot can't hit the controller, which should make sense. Because the controller is the computer that's running the robot, and you get over there and you hit it, and you could cause squirty things to happen, right? So the controller has to be outside of the reach of the robot, which would be the maximum space, right? Pressure sensitive mats. Some old grocery stores still have these around. When they first came up with automated doors, they put these pressure sensitive mats on. And you can still see these stores because they'll have rails on the doors, so you have to walk across the mats. And when you walk across the mat, it makes a connection, and then of course it opens the doors. These pressure sensitive mats are really neat. It allows you to open up the work cell, but the problem is they're pretty expensive, and they've got to be bigger than one stride. So that means you can't step over. You can't have one small enough for somebody to do what? Step over. But these are pretty neat in that what we can do now is we can open up the workspace, and if anybody steps on one of these mats, then it will stop. Light curtains, these are very, very popular. A light curtain is just nothing but a lot of lights, infrared lights. You can't see them if you look at them because they're infrared. And then it shoots beams across, and then we have a bunch of photo detectors over on the other side. And it forms a curtain. And if you walk through that curtain, then it's going to detect you out. And what's nice about that is that if we got carts and stuff that need, or rails or something coming in on a slide that needs to come through the light curtain, when it gets up to it, you can disable the portion that that thing occupies and move it in and drop it off. So these things are pretty popular. And plus you can use mirrors. The only problem we have with these, if you're operating them in a really dirty environment, you need to clean them off because all of a sudden you'll say somebody is there and there's not really there because something's screwed up your light curtain or got in the way. So dirt, these things are susceptible to dirt, moisture. So if you're in an environment where you go from hot to cold and you have condensation, then that'll cause you problems with your light curtains. Pressure mats don't have that problem. But light curtains can cover a lot of space. So we can have basically one set of transmitters and one set of receivers and then bounce it around the outside with mirrors. And we can protect the whole space and still have the space be open. Are you okay on light curtains and pressure mats? We had a KUKA. Our Mercedes was putting on a family day, and they were going to let the family of all the employees that wanted to come down. And the robotics division or KUKA wanted to do something, but they couldn't do anything with a big production robot. So they came down and they borrowed our KUKA work set, and they took the the back door off, and I'll show you all the video. And they put a tray in the front, and they put Skittles in it. And when the people would come up, or the kids would come up, they'd take a cup out and put it in a thing. They'd step on a pressure mat, and then the robot would go up there and scoop them up some Skittles and fill up their cup with Skittles. It was pretty cute. But so they use pressure mats down there. Proximity sensors located in the robot arm could be utilized as level 3 sensors. So level 3 sensors, these are the sensors that come into play when you're in the reach of the robot. Level 1 means you're just inside the work area. So you come through the fences, which is your level 1, which is the actual fences we put around them, or the light curtains. Level 2 would be when you come into there, and the level 3 when you get into the reach of the robot. Completely shut down robot upon detection of intruder, activation of warning alarms, reduction of speed of the robot to a safe level. Now this is becoming fairly popular, because here the robot didn't go out of production, but it slows down enough so you can get out of its way. So instead of knocking you, it nudges you. Directing the robot to move its arm away from the intruder after a collision. Directing the robot to perform tasks away from the intruder. And I don't know about that now. There's another safety monitoring called a fail-safe. These are not my PowerPoints, by the way. This is they gave us these PowerPoints when we had a training session on the 1506 standard. These are the PowerPoints that were presented to us. So if there's any errors in here, which I had seen, we just don't get. There's not liable for that. Let's see, so there's another safety monitoring called a fail-safe hazard detector. The concept of this detector is based on the recognition that some component of basic hazard sensor systems might fail, and this failure might not be found out until some safety emergency occurred. The fail-safe hazard detector is designed to overcome this problem. So that's kind of like the fifth computer on the show, right? And that's what it says. Most industrial accidents that occur are the results of unsafe acts by workers, properly trained operators, careless programmers, or operators activating the wrong controls. And we see that a lot. Component failure of other unsafe conditions. So this is why whichever robot you're working with, you need to become familiar with that teaching. And every one of them is a little different. Even though they do the same thing, every one of them is laid out a little different. And you can see me when I go over there, a lot of times I know the button's there, but I got to do what? I got to find it. And that's unfortunate, but And these are the hazards: being struck by a moving robot while inside the work envelope, being trapped between a moving part of the robot and another machine, being struck by a workpiece, tool, or other object dropped or ejected by the robot. So these guys are moving things around, and you drop them. You know, have you ever dropped anything? Not on purpose. So these are gripping things, you know, and sometimes these things happen, and a workpiece, the object itself might be defective, and it doesn't have the exact parameters that the robot needs to grip onto. And it didn't get caught when it came into the work cell. The robot picks it up and drops it. Right? Or the robot slings it. That's why they won't be safe. That's why they like these fences, because fences help protect you. I think they had a NASCAR wreck last year where the fence saved them. Of course, they just had that Formula One driver get killed. They're gonna put cockpits on those things. I guarantee you. They're gonna put shields around those drivers. I think that's what's gonna come up. To erect safety barriers around the entire parameter of a workplace. A guard containing a sensing device that automatically shuts down the robot if any person or object enters its work envelope can be effective. To put sensitized doors and gates in the parameter barrier that automatically shut down the robot movement when they are open. I'm going to make a point here. This is not when the robot is in manual mode. All of these are when the robot is in the automatic mode. Because when it's in automatic mode, the robot motion is turned over to a program. In the manual mode, the robot's motion is being controlled by the program. Now, what we have the ability to do is we have the ability to run a program in the manual mode. Most of the robots, the FANUC and the Motorman, limits the speed in the auto mode, so they don't have a high-speed teach. The KUKA has a high-speed teach. If you use a high-speed teach on the KUKA and you set it to 100%, then that robot is going to move at the program speed. And they do this, of course, to verify pass and also to figure out the cycle time. The problem with the KUKA is you're going to have to use high-speed teach, because if you use regular teach, if you put it to 30%, it's not 30% below 250. It's going to be 30% of 250, which is the robot moves really slow. So that means on the KUKA, really slow. We'll be over there 5 minutes watching it run as just a standard program. So on the KUKA, to get your speeds like everybody else has, you will have to set it to high-speed teach, but honor the speeds that I tell you to run it at. Okay, you understand that? So if we say 30%, everybody else's robot, if they put it on 30%, that will be 30% with a maximum of 250 millimeters per second. On the Kuka, if you put it at 30%, it's going to be 30% of 250 millimeters per second. So what that means is you'll have to use to not spend all day and have the ability to do the same labs that everybody else does. You're going to have to, when you go to the teach mode on that robot, you'll have to put it on high-speed teach. But realize if you set your speed on the auto mode to 100%, then the robot is going to run it 100%, right? You understand that? Okay. When you jog it, it's still going to be limited to 250 millimeters per second. The problem that we have is that when you switch it to auto, they don't set a maximum speed of 250 millimeters per second. They drop it down a percentage of that. So when you run your programs, it's real slow. So every one of these is basically not talking about the auto mode. They're talking about the what? I'm not talking about the manual mode. It's talking about the automatic mode. When you are in the manual mode, you can be in the work cell with the robot for obvious reasons. There's no way in the world you're going to be able to position the robot perfectly without you getting in there with a tape measure or whatever, right? You understand, and be at the robot. It's just impossible to do an extremely accurate program when you're 30 feet away because everything looks different. Safeguarding. Safety training, dependable machine design, we don't have to worry about that. High reliable controls, we don't have to worry about that. Proper layout of the work area, we do have to worry about that on the big Fanuc. Of course, y'all see what we do on the Mitsubishi. We just run that sucker so slow. We just run it real slow. The robot could actually run faster, but it's not safeguarded. On the Mitsubishi, by the way, is the one on the manufacturer. Safe positioning and clear visibility for programming, we have that. Establish proper maintenance procedures. We'll talk about that if you take the industrial robotics course. Adequate installation performed in the presence of safety personnel. We didn't have to do that because we bought ours as work cells. Obeying safety rules and regulations and authority of organization, and that's what we're talking about now. So y'all got any questions here? So we're going through our safety training, and then the rest of that, basically, we're really not going to deal with in this class. Are we okay? Any questions?
You said on the computer that you will have to
when you got it in manual mode and you run the program, so once we get through with the jogging, we're going to start basically playing around with programs. And we start at the start, naming programs, how to name them, and how to create them and stuff like that. Very simple programs. The problem with the Kuka, if you have it on standard teach, which is limits you to 250 millimeters per second, well, all the other robots, if you put it on, if you play the robot, if you play the program, it's limited at 250 millimeters per second. But if you set it at 30%, it's 30% of full speed, unless you get above 250 millimeters per second. And then so it's limited. Y'all understand that? On the Kuka, if you put it on regular teach, you're limited to 250 millimeters per second. But when you run your program in manual mode, it's going to be 30% of 250 millimeters per second, which is nothing, right? Understand? So you can run yours at the same speed as everybody else. You'll put that robot on what we call high-speed teach. So you got two T's on that pennant. You got one that's got one little error on it. So when you go on your mode select. So our robot has a mode selector on the teach pennant. So the Kuka has 4 positions. It's got one that says, I don't remember where it's at, but it's got a T, and then it's got a circle around it, and it's got 1 error. And then it's got a T, and it's got a circle around it, and I think it's got 3 errors. So which one would you think would be high-speed teach? 3. These are your teach modes. All the other all the other robots has one teach mode. You put it on teach, or you put it on manual. Those are the same. We'll use the term teach. And then you got another mode where you play the robot. I can't remember what it is, but it's up here. It's called play or auto mode. And then you got another one up here for remote. So that means your robot has 3. Your robot has 4 modes of operation. Everybody else has 3. Where you'll have remote, play or auto, and then you'll have teach. Remote means we turn the control. A lot of those videos you saw, the people didn't use the teach pin. If they had a panel up there and they had hit play or stop or whatever, that's what we call a remote panel. So a lot of times they don't even make the teach pin available to the operator, because they don't want the operator to be able to select programs. They don't want the operator to do things that could cause things to happen. So what they'll do is they'll set up a remote panel that has very few buttons on it. It usually has a run, and it has a stop, and then it has fault indicators where and then you usually have a button on it. You can reset faults on it and stuff like that. So if you go into the work cell, then you get a fault. Well, when you come out and close the door, according to this, the robot can't take off when you close the door. Yeah, you have to reset. So you can reset the faults. And this will be on just a pennant. So these guys, and it has an emergency stop on there. So these guys don't have control of that teach pennant. So every one of these robots has what we call a remote on it. And that's what the remote is. That means if you set up a remote panel somewhere. So we call it teach. Some of them calls it auto. Some of them calls it play. That is the mode. You switch that robot in, and now you've turned that thing over to a program. While you're in the manual mode, even though you can run programs in manual mode, you're going to be limited to speed. It's just on the Kuka, when you set 30% now, it will be 30%, like everybody else will. So be careful and don't put it on full speed. Don't put the speeds up to 100% on that robot, because if you do, it's going to run at 100%. So those are the 3 modes of operation. What are the 3 main modes? Teach, auto, and remote. It's just that some of your robots has 2 teach. So when y'all saw, did I move the big? Did I run the big Fanuc for you in here? Well, that was high speed teach. So when I jogged it, it was still 25 millimeters per second. But when you saw the robot move, it was running at full speed. But I had the teach pennant in my hand with the emergency stop, or the e-stop button, not the e-stop, the dead man switch was in. So if somebody would have jumped out there, all it would have been would me just release the thing, right? So we don't run that thing in auto mode because it's not safeguarded. Unexpected robot movements are the concern of employers for obtaining other guidelines. Researchers have developed many guidelines. If a robot is not moving, do not assume it is not going to move. And we demonstrate this over on the manufacturing line. If the robot is repeating a pattern, do not assume that that's the pattern it's going to do all the time. Always be aware of where you are in relationship to the possible positions to the robot that may reach. And this is true no matter where you work. Be aware of your surroundings. When we worked out at U.S. Steel, the electronics shop for the cube ops was up on the same floor as the cube ops. And you literally walked out the door onto the cube op floor. I mean, there. They had scrap haulers that had tires on them that wouldn't even fit in this room. When you'd walk out the door, and what if was sitting there idling, you'd be looking at the bottom of the hub. The tire was up there. And so what you learn in overhead cranes all over the place, radio controlled overhead cranes, or the operator's down here somewhere, and he's running the crane up and down that thing. So you learn real fast when you walk into some place, you look, before you walk out in that place, you figure out where everybody's at and everything's at, because there was 1,000 ways to get killed out at that plant. But it's going to be your fault, just because you were walking around with your head where the sun don't shine. I don't know what that means. So be aware. Be aware of what's going on. You know, I can understand conversations, but don't be doing things while you're, you know, be aware over there. When you got those doors open, you know, be aware of the people that's around you. And if somebody reaches into that work cell, you know, be aware over there. These robots here it's highly unlikely that they will kill you. But, you know, we can break fingers and stuff like that in here. But if you get in front of one of those big old guys, like that big Fanic over there, that sucker will spit you out for lunch and kill you and spit you out for lunch and knock you around a little bit and never know it. Be aware of your power. Y'all see lockout, tagout. Y'all understand that? And of course, we won't need to do that. We're not doing any maintenance on these robots. But if you do the industrial class, we'll lock out, tag out. So our disconnects are capable of being locked and tagged. Most of them have like 3 locks you can put on there, and then that guy showed you how he has that extender you can put on there and put up to 8. So, and the locks have to be keyed. They can't be combination locks, because combinations get around, right? Keys don't. That's not true. They shouldn't. Teaching, program, servicing, and maintenance are my only authorized reason for entering the work cell, so we're okay there. Before activating power to the robot, employees should be aware of what it is programmed to do, that all safeguards are in place, and no foreign material are present within the workplace. And we're going to be doing that. We're going to be putting stuff paper on there, and you need to keep your workspace clean, right? You understand that? We have boxes that we'll put in there. We need to, you know, keep those things out if we're not using them. Don't put them back in the back of the work cell or put them in there. Before I notify supervision immediately when an unexpected interruption to the normal robot cycle occurs. Of course, I'm supervision. Report any missing or effective safeguards to supervision immediately. Check all safeguards at the beginning of the shift. Of course, safeguards, you can check your emergency stop. By the way, I need to tell you that, and I'll show y'all how to do it. Once y'all learn how to do a little bit of programming, we'll show you how to park these robots. What we do is every one of these robots has a battery in the robot. And what that battery does is it keeps up with what we call the point of origin. The point of origin is where all your programs are recorded relative to a point of origin. If the robot loses its point of origin, then no program's running, because the robot does not know the controller does not know where to start from. And we'll talk later on why they do that. And it's in that manual if you got that far. So what we do is we park the robot at their point of origin. We can't afford to keep all these spare batteries and everything around here. They're very expensive. So we park the robot at their point of origin. And if the power fails, then we can come back and remaster the robot. We'll show you how to do that. Y'all won't do it, but you'll be able to do it in the industrial. We'll recalibrate the robot because it's parked at its origin, and then you'll be able to take off from there. If we do that, then aligning the robot is, especially the ABV, but it's not working. It's not an easy task. It just takes a little time. But here, all we have to do is just reorigin the robot. Then we can put new batteries in there, and then or use it that way until we can get new batteries. That's why we like the Fanics. The Fanics, The small FANUC, 200 IC, uses C batteries, alkaline C batteries. The big FANUC uses alkaline D batteries that you can get anywhere. All the other robots use proprietary batteries, so that's why they cost them. Safety is an important component in industrial automation. Robot safety depends on the size of the robot work cell, its speed, and its proximity to humans. Safety sensors and monitoring provide the capabilities of the work cell controller and its sensors to monitor the operation during unsafe conditions in the work cell. Safeguarding is the prevention of injuries or accidents in the workplace. And so safety, what is safety? What is safety? Just safety. Not applied to, Well, we can't prevent hazards. Hazards are all over the place. We can't prevent, we can minimize them, but we can't prevent them. So there's things out there that can cause accidents, even in here. There's hazards in here. Now, they showed that kid on the news that was turned around and stumbled and put his hand through a $1.5 billion painting in a museum. It's true. Because there was a hazard. So he was turned around and walking backwards and hit the edge and fell into that thing. So that's a hazard. So we can't prevent hazards. Safety is what we do to avoid accidents. Safety rules are the procedure we follow to be safe. Right? A hazard is something that gives us a potential for an accident. So these roof tiles could be a hazard. So what can happen? They could fall. In fact, I think we had one fall over there. They finally came over and replaced it. So, of course, and then an accident is when something actually happens. And then we have to fill out an accident report. We have to call security over here. If we didn't have to transport you in an ambulance. This is one thing that's very important about getting your tuition paid. Even if you do not have insurance, you will be insured while you're here. And that's part of your tuition. We okay? Any questions before we go back over there? So what we're doing is working on experiment number 1, which is going to allow you or just get you used to jogging your robot. Of course, we had a few problems. First lab, I let y'all get by with a lot, but you need to learn. You need to learn the direction of your robot when you jog. Okay, you understand that? So we had problems. I'd say I want to go this way, and you'd go the other way. That'd be like driving your car and wanting to turn left and you turn right. That could cause big problems, right? So learn the direction of your robot, and it's hard on the joint jog, but once you get into your Cartesian jogs, that's when you realize the power of those things. Okay, now take a 10-minute break and we'll come back and go to lab.